So moving forward, let's go ahead and jump into our next 2D toolpath, which is going to be our 2D adaptive clearing. Now this is a chip thinning toolpath, and we will go over chip thinning in an in-depth course all of its own. For our tool, I'm going to create a new tool. I'm going to select this new milling tool tab down at the bottom. You can see it's automatically set up the number of the tools sequentially from the first tool. We have a tool 1, so now we're going to have a tool 2. It's going to be a carbide tool. In the description, I'm going to go ahead and use a 3/4, 3 flute, carbide end mill, and again, I like to abbreviate everything. It's going to have an 1.5" length of cut. That's LOC for length of cut. It's going to be for aluminum. And this is going to be an adaptive toolpath. And it's important to note that because I may use this to finish contouring as well, and the feeds and speeds are going to change there again, as I showed you in the last toolpath how to set that up. I'm going to copy that information, paste it down here in the comments so it shows up in the program. Move into my cutter. Now this is not going to be a bullnose end mill, this is going to be a flat, sharp end mill. Now it's set to millimeters. If I'm working with inches, I can click the units down here and change that, as this has an 1.5" length of cut and more than likely an 1.550" of clearance just past the flute. Shank diameter is going to change with the diameter itself to 0.750, and it's going to be hanging out of the holder 1 3/4". You'll notice that the graphics over here changed with that setup, and I'm going to go into my feeds and speeds. Usually what I will do is go ahead and use a calculator, but in this instance I know what I want to do for my speeds and feeds, and once again I'm going to go over that in a separate class. So I'm going to go ahead and do 10,000 RPMs at 200 inches per minute at 100 inch per minute ramp feed rate, a 60 inch per minute plunge feed rate. I'm going to select OK to that, and now I have a separate 3/4 inch cutter that we're going to use to rough around this tool and clear the majority of the material. I'm going to right click on this, copy this tool, add it to my aluminum tools, just to keep building my tool library. And the bigger that my shop gets, the more that I use HSM, the more tool paths I'm going to have. That description becomes more important, and the easier and faster programming is going to be in the future. I'm going to select that tool, feeds and speeds get populated, move over to my geometry tab. Now what you'll see is that it gives me a couple of different options. I now have a geometry option. That's asking me to select what I want to machine as my pocket, basically, to be able to clear material. Now you'll see what I've selected is the outside profile, and it shows me where the stock contours are. If I select that stock contour, that just solidifies that it's going to be machining that. Now if I select this arrow and change the direction, that blue hue has changed to the inside. That's going to create a 2D pocket. Because this is a 2D toolpath, it's allowing itself not to be as model smart. It will allow itself to violate the toolpath. It's just thinking in two-dimensional shape. So I'm going to stick to the outside profile of that toolpath so that it's machining all of this pocket geometry outside of it. Stock contours isn't necessarily need to be on, but it's a good idea to allow it to define what stock is remaining. I'm also going to come back into my geometry, and this is a good time to actually point out how the selection modifiers work. If you see this arrow that's pointed here for the pocket selection, it's not blue at current time. This stock contours is blue. So if I were to come in and actually select geometry, that's actually using that stock contour. So I'm going to red X that out. I'm going to depress that button, now shown in blue, and add our 2 bores to be roughed out with this geometry. And you'll see that that is now represented by that light blue selection with the dark blue boundary that it's contained in. The final geometry selection capability is actually tool orientation, and that is to select multi-axis features. We're not going to go ahead and use that or tick that box at all. When you do, you can see it truncates down. However, we're going to leave everything from our WCS as selected. In our heights tab, this is where we can come back again and change our heights as we want to use them. Now, by default, a few toolpaths default the bottom height selection to selected contours. And this is kind of nice in the case of pocketing, but in our instance we're actually machining a boss feature, so this selection isn't what we want to have as our selection. But as our default, it's a good idea to keep it as selected contours so that if we can select multiple depths, it will automatically change with it. I'm going to go ahead and select the model bottom for this, and we're going to add an extra negative 0.05 millimeters just to get past the model with the cutter. And there you can see the extra just past the model just to get the cutter past that. For the top offset, we're going to stick with model top instead of stock top, as we've already cleared off the majority of that material with the face tool path. We'll have a 0 offset for that. We're going to move our retraction from our stock top to our model top as well. And you'll see that these graphics are updating accordingly. And the cool thing about HSM is I can use this mini toolbar, or I can actually come in and drag and drop if I wanted to. So again, I'm going to change this to 25.4 just for my clearance for safety. 5 millimeters for my retract height, and move on to my technology that's in my passes tab. And you can see this has changed quite a bit from the face tool path. Now we have our tolerance again, but now we have an optimal load. Now this is the amount in which it is going to engage radially with the material that we're going to remove. Now this is an important calculation when you're using chip thinning. I'm going to leave this as default for now for this purposes of this demonstration. It's going to be actually a little bit bigger. With aluminum, that's probably an acceptable number. But this is a calculation that you would want to use a calculator for to be able to actually calculate your true chip thinning capabilities and your material removal rate properly. Minimum cutting radius, that's going to be the smallest amount it's going to try to eat into the corners. In this case, it's almost set to 2 millimeters. I like to kind of keep this around a 32nd of whatever tool diameter I'm going to do. That way we're not actually trying to force a larger cutter to do something too small. In this case, I'm just going to go ahead and put 5 millimeters in there. It's not necessary because we're going to be machining a boss, not a pocket. Now, if I was going to be doing a pocket, I could use slot clearing, and this is, if you hover over this, you can kind of see a demonstration of what that would do. That would go ahead and allow it to clear a slot out to be able to remove material quickly by engaging a larger profile throughout the majority of the pocket clearing. We're not going to be doing that. I'm not going to be doing multiple depths. I believe I might have enough flute length to go ahead and just go straight to the bottom on this. We're going to be using stock to leave, as this is a roughing tool path. We're going to leave 5 millimeters on the stock as the default. We're going to go to our heights tab, and you'll see that some of the things within the heights tab have changed. Now we have the ability to ramp in and out of a pocket and control over how it's going to engage itself into material. In this case, once we're outside of it, we're going to go ahead and just switch that to plunge. I don't have a problem plunging outside of the material, and that's how it's going to allow itself to clean this part up. We're going to not lift at all, but this is going to be the amount that it lifts up, and this is our stay down level. I like to stay down the most in an internal pocket and the least in an external pocket. Now the reason for that is if I need it to clear something, I want it to know that it's safe to come up and over the part to save time versus trying to travel around the part, because that's what it's telling it to do. It's telling it to create toolpath, and it's going to create toolpath in a section, and if it needs to move to another side, if it's at most stay down, then it's going to try to feed itself all the way around there. Now it may be a fast feed rate, but the fastest distance is still for it to wrap it over to the next point. So I'm going to leave this at least. I've changed my ramp. I'm going to change my lead in, lead out. Again, I'm not going to use the vertical. I'm going to set that to 0. I'm going to hit OK, and it's going to calculate our toolpath. Now what you'll see is it's allowed itself to go down into our pockets and machine. One thing I did do is I may have cleared this out, and it's set at its depth. And since it's a 2D pocket, it's violating the bottom of that pocket. So I'm going to have to actually come back in here, edit, go to my geometry tab. I'm going to hold Control down, left click, and unselect that hole. I'm going to hit OK, recalculate, and just like that I was able to take that pocket out. So now I only have it clearing out and roughing this bottom pocket. Now here's the problem. You'll see that I had set it to plunge, and we're going to now plunge into all this material. Well, that's not exactly safe. Again, I'm going to edit my toolpath, come into my linking, switch from plunge to helix, and this is where some of the intelligence comes into HSM, is that it's going to plunge where it knows it can outside of the material, and that's been told to this by the stock contours. And then it's going to helix only where it's going to engage material. That's because both things are defined perfectly in HSM. It knows there's stock, it knows there's a part.